So before I start, how many of you have heard of NIST or familiar with it? Pretty much everybody. I'm still going to cover what it is because it's that part will be a little bit boring maybe. Let's see. So just a brief outline, I'm going to talk a little bit about what NIST is. We're going to talk about the definition of agility. Usually Craig is the one that gives this presentation, but he couldn't make it, so I'm here. We're doing a little bit of work within our group in IEEE, and I'll just cover what that is. I'm not going to go into these specifics. Then I'm going to talk about our webpage that we're working on, and then I'm going to specifically talk about the work that I'm doing. So George Washington made this quote: "Uniformity in the currency of weights and measures of the United States is an object of great importance and will, I am persuaded, be duly attended to." So from as early as 1790, George Washington had this idea about standards. And I always make this joke that he didn't say anything here about NASA. And then I also make the joke that we like to have this rivalry between departments that use the same font, but we really don't. So NIST is a really big organization, I guess, compared to some other organizations. We have over 2,900 different faculty and staff. 400 of us are involved in over 1,000 different national and international standards committees, obviously, because we're NIST. So now the work that my group is doing. So obviously our group is called Agility for Robotic Performance. And when we talk about agility, what we really mean, just to kind of summarize this, identify recovery, automated planning, having fixtureless environments, swapping between robots and manufacturers with minimal amounts of change. But really, if I was just going to sum that up, it's about robots being intelligent, dynamic, and robust to a dynamic environment. And that's really what our work kind of centers around. So I said I was going to talk a little bit about our IEEE standards work. Anthony Downs is the person that's mainly working in this area. I'm doing nothing. If you have a question, I have some of his contact information at the end, but it's on the core ontology of robotic systems for industrial robotics. Something I am involved in is ARIAC. How many of you have heard of the agility competition that we have? Okay, excellent. So we have a competition. We've given over $17,000 in prize money. And the participants have ranged from academia to industry to just private, normal people working in their basement. And they've actually been able to win. So if that is something that sounds interesting to you, I encourage you to participate. It's been going on for 6 years, 5 years of those, we've been actually doing the prize competition. And we've had a lot of different kinds of scenarios. We've done kitting, we've done multiple robot arms. And this is the one thing I'm going to talk about where we actually use ROS. So we've done multiple robot arms. We did a scenario recently that was creating assembling a ventilator. So we try to keep that fresh, try to do different types of scenarios. And each one of these scenarios, we have what we call an agility challenge, where robots will drop parts or we won't be able to sense different things. And that's how we score the competition. So if you're interested in that, there'll be some contact information at the end for that as well. So we also are really interested in the artificial intelligence community for industrial robotics. Mr. Pavel Palavchuk is in charge of our AI website. And then there we talk about different data sets that people can use if they're interested in using machine learning for artificial intelligence. There's also different learning tools. We do different blog articles about some of the work that we're doing and some of the work that the community is doing. This is a great resource if you're involved in deep learning and industrial robotics. This link will also be at the end, and it's also obviously in the uploaded presentation. So let's talk about the work that I'm doing. This is the only part that I actually know anything about. Everybody, the rest of everybody else is nice. So as we move forward, NIST is all about measurement, right? But as robots become more and more intelligent, the way we think about measuring those robots' abilities are different. right? In a highly dynamic environment, it's no longer feasible to test every single scenario that the robot will see, right? And then from this perspective, now we need to think about what does the robot conceptually understand, right? What does the robot understand itself, and how do we measure that? How do we figure out what that is? And then how do we train these, I'm coining this term, hyper intelligent robots? How do we really think about what that is? So that's kind of the work that I'm doing. So how many of you are familiar with autoencoders? Okay, so how many of you are familiar with neural networks in general? Okay, great. So autoencoders are just a type of neural network architecture where you take something of high dimensional space, like an image, 256 by 256, you reduce the dimensionality down to something much smaller, and then you basically upscale it to something bigger. And that means that you can express an image, for example, in something much smaller, and you can understand, the model understands and learns things about that image that you don't necessarily even intend to, because it's unsupervised learning. Just bear with me, I needed to say that for you to understand where we're going with this next. So the work that we're doing now is based on a paper by Mr. Professor, probably Sotomayor. And in his paper, they use, this is for robotic perception. They have different parts and they run them through these autoencoders, and they create what's called a latent vector. So there's just a vector that's associated with each part that they run through this autoencoder at different angles. So for every part, there are multiple different orientations. Each orientation has a latent vector associated with it. And then the idea is that you can then take this image, these sets of images of different orientations, and do a nearest neighbor mapping when you show that model a new orientation. So this is just pose estimation. We do pose estimation in a lot of different ways, but it turns out that autoencoders are really good at low resolution. They're really good at dealing with occlusion, different lighting, because you can train that kind of robustness into it. So that's what Sotomayor's doing. But the question that we really want to answer now is, did the model learn about the part? Or is it just looking at these pixels and kind of mapping? Does it understand that all these pictures sum up to an object that actually exists in three-dimensional space? So how do we do this? So I spent almost probably 8 months trying to figure out a way to approach that. So it turns out that if you look at the latent space and you see how the model organizes that information, yes, in fact, the model does understand that it's looking at a rigid body, which is really amazing. Right? We only showed it pictures of rotating objects, and it was able to actually understand that it was seeing a rigid body. So how do we do that? Well, in the latent space, remember we have these different orientations of the same object. And we look at successive orientation. So we rotate the object by a degree, we plot it in latent space, it's n-dimensional space. So the approach that we use is not, it doesn't mean it has to be 3-dimensional or 4-dimensional, it's n-dimensional because we use the B-spline. So we rotate an object by a few degrees, plot, rotate an object by 3 degrees, plot, rotate an object by 3 degrees, plot. And we look at that profile in the n-dimensional space, and then we measure how smooth it is, and then compare that to like a random set of numbers. And we see that the model actually does, in fact, understand that this is a rigid body and that it has rotation, which is astounding, right? But actually, if you really think about it, that's how we understand what rigid bodies are. We look at an object, rotate it, and we understand, okay, this is a rotating object, it must exist in 3-dimensional space. And it turns out that the model has a similar understanding with a similar treatment and training. So why do we care about any of this trying to understand latent spaces and environments? So before I talked about hyper-intelligent robots, right? So for very intelligent robots, we need a very intelligent environment to test, train, and understand those robots. So our work is now looking at how can we use neural networks and latent spaces and generative networks to understand and create intelligent environments that can train and test robots. So the brute force way to do that is to create a procedural environment that creates multiple different permutations of the same environment. Has anybody ever played No Man's Sky? All right, this is a good crowd. Okay, so and if you haven't played No Man's Sky, it's a procedurally generated video game with millions and millions of planets and flora and fauna. And we can apply this idea to environments to try to test robots. However, this is not really a tractable problem because you have so many different permutations. But this is a good place to start. The next idea is to have the environment controlled by another robot using reinforcement learning. So in this case, this is a paper from OpenAI where they use something called asymmetric self-play. And in this case, a robot called Alex, they call it in the paper, they call Alex, creates the challenge that the other robot has to solve, named Bob. So the genius of this is that Alice, whatever challenge Alice creates is solvable because Alice is also a robot. So now we have an intelligent environment training an intelligent robot. And then the end picture of that is we talked about using a procedural environment for this. We talked about using a reinforcement learning controlled environment. But what if we used a GAN? How many of you are familiar with GAN? Generative Artificial Networks. Okay, it's a way for a neural network to compete against another neural network and create completely novel environments, right? So how can we use this technology to try to train a robot? And then how can we look at the latent space? Say I'm coming back to the latent space. How can we use the latent space to explore what the environment understands about the robot? So that was my research. If you are interested in learning about reinforcement learning for industrial robotics, our prep student is going to give an amazing workshop in August 29th to 30th this year. So if you're interested in getting started with reinforcement learning and you want to apply that to your research, this is a great place to start. And if you would like to contact me, here's my contact information. Yes.
So where was that workshop? Was it online or?
It will be online.
Okay.
We're also trying to put it in person.
Okay.
Yep.
So TBD.
Hmm?
TBD on location.
Yes, definitely to be determined. So the website, if you're interested in the website, this is the link to it. This is also going to be online. And if you're interested in ARIAC, this is the information for ARIAC. If you have any questions, I'm here to field your questions.
All right, thank you. Any questions for Willie? They'll be here all day, so we're most there. Oh, we have one?
Have you had any opportunities to do accuracy studies for the 3D reconstruction of the body in the latent space compared to benchmark tests quantified based off of latent space modeling over an image to a body image?
Right. So
You can summarize the question.
If I understand you correctly, have we done any comparison studies between our latent space information and reconstructing the other reconstructive technologies?
Just the overall.
Right. Yeah. So the interesting part about what you're saying is, so the autoencoder that we use does not reconstruct the object in its entirety. It only gives the location, right? So they train their autoencoder to give the location, and because it's trained on a specific part, they know what the grasping is like for that particular object. So it's not actually reconstructing the object as a whole. Does that make sense? Okay. Any other questions? Yes.
So when you're talking about linked spaces, when the autocomplers generate these what vectors come in, you said in dimensions, are all going to be the same dimension?
Yes, yes. So I say n-dimensional because when we reduce it to whatever reduced dimensional space, that can change depending on how well the autoencoder performs for a specific object. It might be 4, it might be 16. And that was the hard part, trying to figure out what's the best way to analyze that that's not dependent on dimension.
So what's the difference between the same object, two different autocomplers? Numbers substantially better or worse?
So I think in general, it's better, but I like to reduce it as much as possible. But that's a good question. And it's probably,
Yeah. Bringing it back down dimensions.
that's part of it. And also the computing involved in trying to understand it is a lot more complicated. When I was doing this was for the manifolds or anything more than 3 dimensions. So it was a little bit mind-boggling. Actually, how much time do I have?
A couple minutes.
Okay. So I was doing this research, funny story, and I was telling my friend about it, and I was pontificating about n-dimensional space. And she said, "Is it weird that I can't picture what you're saying?" And I was like, "Absolutely, that's not weird. Nobody can picture 5-dimensional space." I thought that was going to be funnier. Anyway.
Trying to picture 5 dimensions.
Is there a correlation in these objects that have a lot of symmetries? Body has a lot of symmetries.
Mm.
We can compress a lot of our understanding of information. By the symmetries, something that understand much more.
Right. So the question had to do with, do we see is there anything we can do with the fact that objects tend to have a lot of symmetries, right? So it turns out that one of the strengths, and they cover this in the Sundabar paper, is that symmetries don't make a big difference here, right? For the purpose of trying to grasp or understand where the object is, they're simply doing a nearest neighbor matching. So if the symmetry doesn't matter, then the autoencoder doesn't care, and then the grasper actually doesn't care as well.
So thank you. We'll be here today. Feel free to